Welcome to this video tutorial on finite element analysis, a practical approach using ANSYS. So myself, I am Shankar, Assistant Professor of Mechanical Engineering from Tyagarajar College of Engineering, Madurai. So before starting our tutorial, let's see the steps involved in FEA analysis using any FEA softwares. So basically it can be classified into pre-processing, processing and post-processing. Under pre-processing, you have all these steps which are required to be done by the user, and processing of solution which will be done by the computer, and finally you can see your results in this post-processing, right? So this is a series of video tutorials. So far we have seen our 4 exercises, and today we'll be seeing this 5th one, which is analysis of maximum stress induced in a bar due to discontinuities. And this is going to continue further. We are going to see some thermal analysis, some dynamic and coupled analysis in our upcoming video tutorials. So basically, today's problem will be concentrated on. So before getting into this problem, okay, let me tell you some introduction about this. So our 5th exercise, which is analysis of maximum stress induced due to discontinuities in a bar. So you need to understand what are discontinuities. So the discontinuities are nothing such as the notches, fillets, holes, sudden change in cross sections, sharp corners and regions, keyways, spines, surface roughness or scratches. These are the discontinuities which are present in a machine element. So let me take a simple example. So for explaining my concept, let me take a simple example of a stepped bar. So this section is made up of steel of particular diameter and length, and the second one of aluminum diameter and length, and I have a load 100 kN acting outwards. So the stresses in individual sections, section 1 steel and section 2 aluminum, can be calculated using the theoretical formula, and the value is 35.368 and 19.894. So the maximum stress resides with the section 1, which is of minimal cross section when compared to section 2. So theoretical concept states that the maximum stress is 35.368. But is it the maximum stress actually? Okay, let me check it with the help of an analysis. So this is a 3D analysis of the same problem which I have modeled in ANSYS Workbench. So ANSYS Workbench is one more module which will be helpful to model 3D models, and it has lots of options. So here you can find the maximum value as 51.866. How come is this? But the actual theoretical answer is 35.368, but the actual stress shown by the ANSYS analysis is 51.866, and I have not changed any parameters. I have modeled the same problem with the same load and everything is same. The reason being that there is a sudden change in cross section. So you can find that the maximum stress is concentrated at this location of the change in cross section. Here you can find the same 35, and here you can find the same 19 in the aluminum and steel, but the maximum stress resides at this location of change in cross section. So this is due to a factor called as stress concentration. So whenever a machine element changes the shape of its cross section, the simple stress distribution no longer holds good, and the discontinuity is different. So this discontinuity will cause an abrupt change in the stress, which can be given by the factor called as stress concentration. The stress concentration factor is nothing but the ratio of maximum stress to the nominal stress. So the nominal stress is nothing but this. So this is my nominal stress, and in order to calculate this maximum stress, I need to know this KT. KT is a factor, which is the theoretical or form stress concentration factor, which has been experimentally determined for various configuration and has been tabulated, which is a constant one. I can take it from the table, I can substitute here, I can calculate the nominal stress. If I multiply these two, I'll get the maximum stress. Okay, so we are going to see some cases for which this maximum stress is going to be. So these are the 8 cases, right? So rectangular plate with a hole in tension, shaft with a transverse hole in bending, shaft with fillet in tension, bending, torsion, and groove to shaft in tension, bending and torsion. We have 8 problems here, and among these 8, in this video tutorial we'll be seeing the only one which are highlighted in red color here, which is rectangular plate with a hole in tension, stepped shaft with fillet in tension, and groove to shaft in tension. These are the 3 things that we are going to do, that we are going to see in the upcoming sessions, right? And all the other things, those are a little bit complicated, which means you have to do only the 3D analysis of all these other black color problems, right? So which is a little bit above the scope of this video tutorial. Okay, so only these headings which are highlighted in red color, they can be simplified into either one dimension or two dimension. So that's why I have highlighted them in red color. So what we are going to do is that we are going to simplify these problems into two dimension, and then we are going to solve. So if you want any more clarifications, you can find it here. So this is the first one, which is a plate. This is a plate of some thickness, and I have a hole at the center. So what is the stress? So, and similarly, the second case, a transverse hole, a shaft with a transverse hole in bending, and this is not we are going to see. And you can see this tabular column for this D by B ratio. D is the hole diameter and D is the actual shaft diameter. If you have this ratio, you can find the KT. So this is already calculated using some experimental data, and similarly you can find for all the other things. So this is we are going to see stress concentration for a stepped shaft with a fillet in tension. So we have the KT values for various R by D and D by D ratios, which we'll see later. And similarly we have the other which is in bending. Similarly this is in torsion, and similarly this is grooved shaft in tension. So grooved shaft in tension. So this problem we are going to see, and the same grooved shaft in bending and torsion, which we are not going to see, right? So this is a short introduction about the discontinuity. So the discontinuities can create a stress which is way beyond the stress that is calculated using the nominal formulas. So that is what we are going to see in this class, okay, in this video. Okay, so the first problem that you are going to see is the plate with the hole, a rectangular plate with a hole. So this is a rectangular plate of width B, and the hole which is of diameter D, and the plate is of thickness T, and I have an axial load acting at both the ends, right? So this is my problem. So I'm going to model it with the help of some values which will be helpful for me to solve. So this is the problem that I have modeled. So same rectangular plate, and I have loading acting on both sides. B is the width, W is the length, and D is the diameter of the hole. So these are my parameters that I have here. So in order to solve this problem, I'm going to simplify this problem. So you can find that this problem is mirror image. So you can along this central vertical y-axis and along the x-axis, horizontal x-axis, this problem is symmetrical on both the ends. It's symmetrical in y-axis, it's symmetrical about x-axis. So hence I'm going to reduce this problem like this. So this is my actual problem, and this is by 1 by 4th of my problem which I have here. So this line is the symmetry line, x-axis line. This is the symmetric y-axis line. If I have a symmetry along x and y, I can get this entire problem again. So this is what I'm going to simplify this problem like this, a rectangle plate with hole. I'm going to model only the 1/4 of this model, right? So which is here. Okay. Here you can find, okay, so I'm going to select the element. So step 2 is element selection, and I'm going to model this problem as 2D. So I'm going to convert my 3D, actually this is a 3D problem, a plate width of thickness T is a 3D problem. I'm going to convert it into a 2D problem, and the element that I'm going to use is a quad 4 node 182 element, which is plane 182. It is a quadrilateral element, right? So the plane 182 is a 2D modeling, it is used for 2D modeling of solid structures, and the elements can be used either as a plane element, plane stress, plane strain, and axisymmetric. So these three are important terms: plane stress, plane strain, and axisymmetric are three important terms which you have to understand. And this quadrilateral element, it is defined by 4 nodes at each vertex of this quadrilateral, and each of them have 2 degrees of freedom along x and y directions, translation in x and y direction. So these are some of the other properties that this element possesses. Right. Before solving the problem, I need you to understand this concept of plane stress, plane strain, and axisymmetric. So what are these? Let's see in this slide. Okay. So plane stress, plane strain, and axisymmetric, so I can see from the wordings here, plane stress, plane strain, and axisymmetric are nothing but the conditions which are used for converting my 3-dimensional model into a 2-dimensional model. So let me take the first one, which is a plane stress condition. So I have a bracket here which is fixed at these 2 holes, and I have a pressure acting on the top of this problem, and it is of very small thickness, right? So if you consider here, I can model this 3D problem into a 2D problem as shown here, and you can find the strain acting along this z direction. The z direction, it will have both stress and strain in all the direction, but the stresses in this z direction is 0, approximately equal to 0, because I have a very negligible thickness, but the strain is not 0. So plane stress is a condition in which the stress in the third direction is 0. So using this criteria, the sigma z equal to 0, I can simplify my problem from this 3D to this 2D model. And the second one is plane strain condition. Plane strain condition is like this, where I have a very much longer thickness in z direction and I have a pressure acting like this. So here I can model this problem like this, where the stress is not equal to 0, whereas the strain is approximately equal to 0. Because I have a very large length, the change in deflection along this z direction is very much smaller. Hence, using this condition where the strain in the third direction is 0, approximately equal to 0, I can model this problem as such here, right? So from these two conditions, you can find that plane stress will have a very small thickness, whereas plane strain will have a very large thickness along the z direction. And the third one is axisymmetric. From the diagram, it is very much easy to understand that axisymmetric is axis plus symmetric, which means it is only used for object which has an axis, which has an axis of symmetry, axis of rotation. So I can model this cylinder, hollow cylinder like this, right? So with the help of a rectangle with a y-axis, and with this y-axis, if I try to rotate this rectangle, it is going to rotate and create a hollow cylinder like this. So plane stress, plane strain and axisymmetric are three conditions which are used to simplify my 3D models into 2D models. For this problem, I have used the concept of plane stress, right? So the third one is material properties, and here I am not going to have any section properties because I'm going to model it as a 2D problem, right? And then, so this is my modeling of the problem. I'm going to model the 1/4 of my model, and at the same time I'm going to only model the 2D. I'm not going to model it as a 3D, which is I'm not going to model it model the thickness of this problem. I'm going to only draw the rectangle. I'm going to cut out a 1/4 circle at this location. So I'm going to give the symmetry conditions, and these are the coordinate values correspondingly. And here I have a pressure. So here you can find in the problem, instead of load, I have a pressure acting. So P is my pressure here, which is 100 megapascal. So this pressure, as I have simplified my model, as I have given to give the mesh attributes divided into segments, and I'm going to mesh the problems. And next one is boundary conditions. So I'm going to give three boundary conditions. One is this two symmetries, and the other one is this loading condition. So these are my three boundaries that I'm going to give here, right? So now we'll see how to solve this problem in ANSYS. So as usual, you can open the ANSYS APDL from the start menu. You can go and click on ANSYS mechanical APDL to open this mechanical APDL window, right? So in this, click on preferences, click on structural, and click on OK, and preprocessor, element type, add, click on add, and here I am going to give solid, which is quad 4 node, which is the quadrilateral element, quad 4 node 182, and plane 182 is the official name of that. So once you click this, here you have an options. Under the option, you can find the option called as plane stress. Once you click this, you'll have axisymmetric, plane strain, plane stress with thickness, general plane strain, and axisymmetric with torsion. So here I'm going to use the plane stress. Here plane stress, you can find two things. One is the only plane stress, the another one is the plane stress with thickness. So here I'm going to select the plane stress with thickness, which means you have to input the thickness, but you'll model it as only 2D problem. You'll not give the thickness while modeling, but you'll give the thickness at the initial stage itself. Okay, so I'll click on OK and I'll close. Now I'll go to a concept called as real constant. I'll click on add, and I'll click on OK. So here you can find the thickness that is being asked for, right? So the thickness of my problem is it's going to be, actually this is my problem, and I have a thickness T of 30 mm. So I'm going to give my thickness here, right? Right, so I can click here, and the thickness of 30 mm, I'm going to keep the length unit mm, and click on OK, and I'll click on close. Next, I'm going to give the material properties, material models, click on structural, linear, elastic, isotropic, and my X model is 200 GPa and 0.3, but I'm going to give it in megapascal, so 200 E3 and 0.3, and click on OK, I'll click on close. So I'm going to model now. So model, you can model this problem in two ways. Either you can, so this is not my model, I'm going to create like this. So this is my modeling. So there are many ways in which you can model this. So one is you can give these coordinate values, create key points, then join them with lines, then you have to create an area, right? So or directly you can create an area. There are two ways in which you can do this. So it's all depends on your convenience, right? So let me do that. Let me show it to you. So as usual, let me go by the conventional way, which is key points in active CS. So the first key point, which is 0 tab 0 tab 0, and I'll click on apply. So and the second key point, it is 300 0 0. So the second key point, which is 300, apply. And the third key point, 300 200. So the third key point is 300 200. I'll click on apply. And the final key point is 0 200. So the fourth key point is 0, 200, 0. So you can find all my 4 key points being here. So I'll join them with the help of lines. So lines, straight line, I'll click on this one, and I'll click on here, and I'll click on here, I'll click on here, and click on OK. So far I have created key points, I have created lines. Now I have to create areas because I'm modeling it as a 2D. So I'll click on areas and arbitrary and through by lines. So I'll click on all the 4 lines and click on OK. You can find the area being generated. Instead of doing all these things, you can simply directly go to areas, rectangle by 2 corners, and this is the starting point, which is 0, 0. So x is 0, y is 0, and width is 300 and height is 200. So as the width of my problem is small delay here. Okay. So we can find here the length is 300 and the width is 200. So if you directly give this and click on OK, you'll get this same area. So this is a shortcut that you can do directly. Now after modeling this, I need a hole at this location. I need a 1/4 cutout at this area. So in order to create the hole. So in order to create a hole, I'm going to create a circle at this location. So for that, I'm directly creating areas. I'm going for circle, I'm creating solid circle, and my location is 0, 0, and my radius of my circle is 25. If I'm not wrong, the radius is 25 mm, it's given here. So the diameter of my circle D, capital D, is 50 mm, hence my radius is going to be 25 mm, right? And I'll click on OK. So a circle is generated here. Now actually I don't need a circle here, I need a cutout at this 1/4 location. In order to do that cutout, go for operate, booleans, subtract, and click on areas. So be careful here. While subtracting these areas, first click on the area which you need to retain. So this is the area that I need to retain. I'll click on that. I'll click on apply. Then I'll click on the area which I don't need, and then I'll click on OK. So these are two things that you have to do. First one is, I'll repeat again. I'll cancel this. Subtract. Once you click on the areas, click on the area that needs to be retained. Then click on apply, then click on the area that needs to be deleted, then click on OK. So you can find OK. Here you can find the cutout. This is how you do that. So 2 times you have to click, and you have to click on the apply button, right? So first one is the area which has to be retained, then the area which has to be cut out, right? Once this is the stage where the modeling is completed, then I have to apply the boundary conditions. So before going to the boundary condition, I need to mesh the problem. So don't forget the steps, follow the steps as usual. So after the modeling, I need to mesh my problem. So I'll go to mesh, and I'll click on size control, manual size, lines. So I don't need to go for mesh attributes because I have only one material property. If you have multiple material properties, then you may go for mesh attributes. So directly I'll go for lines, and I'll click on all lines, and let me give my number of element divisions, say 100, and click on OK. Now let me click on mesh, let me click on areas, let me click on free, and let me click on this and click on OK. So meshing it takes a little bit of time. So I'm meshing the area. Don't mesh the lines because you have created mesh areas. You are dividing the lines into small segments, but you are meshing the areas. Don't mesh the lines. Be careful in this. Okay. This is a warning. Please ignore this warning. Don't worry about this warning. Right. And this step of meshing, it's called as a non-uniform meshing. So you can find a quadrilateral. It's not arranged in an order. It's randomly it is distributed. So this type of meshing is a non-uniform type meshing. So each and every element will have different shapes and size, right? So there is one more option called as, when you go for areas, you can find this mapped and by corners, right? If you select this, the area, the meshing will be very much uniform. There are certain cases where the meshing needs to be uniform, but as far as my problem is concerned, I don't need to worry about this. So I'll just show it in another video or somewhere else. So I'll just leave it as it is. Then I'll go for loads. I'll click on define loads. There are 3 boundary conditions that I need to apply pretty much here. So there are 2 symmetry conditions. So 2 symmetry condition and 1 pressure loading along this line, right? So these are the 3 things that I need to do. So I'll apply these 2 symmetries at these locations initially. So for that, go for define loads. I'll click on apply. I'll click on structural. I'll click on displacement. In the displacement, you can find there are two things. One is symmetry and another one is anti-symmetry boundary condition. Here I am going to apply the boundary condition called as symmetry boundary condition. On this I am going to select width area. So I'll click on this option. So first you have to select a line about which you are going to mirror this area, or you are going to create symmetry about this area. So first I'll select this line. Right, as I have selected this line, I'll click on apply, then select the area which needs to be mirrored. Select this mirror area and click on OK. So you can find a small yes which is created here. I don't know whether you can see this or not, but there's a small yes that is written at these locations. Again, select with area, select this line, click on apply, then select the area which needs to be mirrored and click on OK. So here again you can find the small yeses. If you just zoom in, you can find that. So far the symmetry has been created. Then I have symmetry boundary condition at this both location. Now I have to apply my pressure. So for that, so pressure is a value of 100 megapascal. As you can find here, the pressure is 100 megapascal. So once you apply the pressure has to be applied directly. You don't have to divide the pressure here. Don't divide the pressure by 2. The pressure has to be, even you have modeled the 1/4 model, don't divide the pressure. The pressure has to be applied directly as it is. So once you have to apply the pressure, go on pressure and click on pressure on lines and click on the line, and I'll click on OK. So here you have to apply a pressure of minus 100. So you can find the value of pressure, so which is 100. So the pressure always takes the opposite of the sign, which is the positive x-axis is actually the negative x-axis is actually positive, and so the sign convention are interchanged in the pressure. So the minus 100 pretty much means the positive x direction, and click on OK, and you can find the right hand side arrow mark. So once this is all done, you have to solve the problem. Click on current tellers, solve current tellers, and click on OK. Don't worry about this, click on yes, and you can find yes, solution is done. So now go for general post processor and click on plot results, nodal solution. So first let me show you the displacement value, which is say 0.155298. It's the it is in that's the maximum displacement, and this is not I'm going to compare, but anyway, save this image, go for plot control, write meta file and save this image. The thing that I'm going to compare is actually the stress. So click on nodal solution, go for stress and click on one meso stress and OK. So you can find the maximum value of stress is 303, which is accumulated at this location. So 303.662. Let me compare it with the theoretical value. So this is my problem. So I have calculated the theoretical. So from this table, my diameter is 50 and my width of my plate, it is B is 400. So 50 by 400, and I'll get the value of 0.125 D by B ratio. And using this 0.125, here you can't find 0.125. After 0.1, you have only 0.15. Either you can interpolate it using the calculator, or else I have plotted these values in Excel and I have calculated the corresponding graph equation. And in this equation, if you substitute the value of D by B for X, you'll get your KT, stress concentration factor KT, in the Y value. You can do this, or you can interpolate using calculator. And this is the 0.125. For 0.125, you have the stress concentration of 2.6515. Now for calculating the nominal stress, which is load divided by area, in this I have to subtract my diameter, because without the hole I have to consider my plate. So the plate without the hole is that I have to subtract the hole from the width of the plate, and the thickness, that is going to be the area. So B minus D into T. So if I do all the math, and I'll get the nominal stress to be 114.285 Newton per mm squared. If I multiply it with the KT value 2.6515, and I'll get my sigma max to be 303.0285, and my ANSYS result shows 303.662, a close match with some little bit of an error, but it's a very close match. 303 is very good, and only after the point the values changes. So this is all about solving a rectangular plate with a hole using ANSYS. Right, so this is, you can compare the maximum stress. So this is for the first problem. The second problem that you are going to see in this tutorial is that here, the second problem is a stepped shaft with a fillet in tension. So I have a stepped shaft and I have a load acting on both the sides, and there is a fillet at this location. It has been welded at this location. A fillet weld has been done here of radius R, and now I am going to calculate what will be the maximum stress in this stepped shaft, right? So I'm going to model a problem with the help of values. So this is my problem. One end of the stepped shaft is fixed. It is made up of steel, and the diameter 400 and the smaller diameter is 200 and my radius is 40 mm, and the length of the smaller step is 300 mm, length of the larger step is 600 mm, and a load of 2 meganewton is acting at this location. So this is all about the step shaft with fillet in tension. So once the problem is modeled, right, so I'm going to simplify this model. So this is a 3-dimensional model. I'm going to convert this 3D model into a 2D model using these conditions that we have seen above. Here I'm going to use the condition of axis symmetry. So this is a cylindrical object, so hence it must have a center axis, and if you rotate this rectangle, so these two are the rectangle, if I rotate this about the center axis, then you will get this 3D model. So this 3D model is getting converted into this 2D rectangular model of this is the larger radius, this is the smaller radius, and this is the fillet radius, and I have the load P acting at this location. So I have converted my 3D model into a 2D model using the axis symmetric condition, and the element that I'm going to here use is the similarly here I'm going to use the same 2D element, hence the element is quad 40182, right, and I have used the condition of axis symmetry in this problem. And as I have already told you the 3 condition, the last problem we have seen the plane stress condition, and this problem will be using this axis symmetry condition. And my material properties, and this is the model that I'm going to create. So 0, 0, 0, this is the diameter of 400, but as this is the radius, so hence the value will be only 200, and the length is 600, so 200, 600, 0, this is 0, 600, 0, 0, 900, 0, and 100, 900, 0. So these are the points, and I have one more point here which is 100, 600, 0, which is this is the diameter 200, hence this point would be 100, and I have a radius of 40 mm fillet that is acting here and a load here. So I'm going to model this problem. Once the modeling is done, I have to mesh my problem, and once the meshing is done, I have to give the boundary condition. The 2 boundary conditions are one is fixed at this region, another one is a load acting at this region. Now we'll solve. Now we'll see how to solve this problem in ANSYS, right? Okay, so I'll go to ANSYS. So I'll delete this problem. I'll start new, clear and start new. Do not read file. I'll click on OK. I'll click on yes. Okay. Now I'll go for preferences, structural. Okay. Preprocessor. So I think you must be familiar by now. So solid, this is a 2D model, so solid quadrilateral element. I'll click on OK. Now I'm going to give the condition of axis symmetric, hence go for options. Instead of plane stress, I'm going to click on axis symmetric and OK, and I'm going to close. So one thing that you have to note is that, so the axis symmetric is here. So this is my axis symmetric. Axis symmetric means my problem is going to rotate about a particular axis. So here my entire problem is going to rotate about y axis. The one thing that you have to note in ANSYS APDL is that once you give an axis symmetric condition, the problem always rotates about the y axis. So let me consider this vertical axis to be the y axis. In ANSYS APDL, you can only rotate the problem using the axis symmetric condition about y axis only, not about z axis or not about x axis. You can only rotate the object about y axis. You can't rotate the object about x or z axis. So that's why I have modeled my problem in vertical manner, right? So please be careful in this, and I'll click on close. I'm not going to have any real constant. I'm directly going to have the metal properties, metal models, and my properties are steel, so which is 200 E3 megapascal and 0.3. So the unit is in Newton mm. Okay, and click on model. So here I'm going to create a first rectangle here. So a rectangle of width 200 and height 600. So I'm going to create this rectangle. So width 200 and height 600, the larger diameter bar. So I'll click on create. I'll directly click on rectangle by 2 corners. So my starting point is 0 and 0. My width is 200 and my height is 600. I'll click on OK. So this is the larger diameter bar, and I'm going to create the smaller diameter stepped shaft, and my location starting point is 0, 600, and my width is 100 and my height is 300. So that is my next one. So again by 2 corners, but my location is 0, 600, and my point is width is 100 and the height is 300. I'll click on OK. So this is my second rectangle. So I can find here width is 100 and my height is 300. So instead of creating these key points and joining them with this line and then going for areas, I have directly created these 2 areas, right? Now what you have to do is that these 2 areas are not separate. Actually these 2 should be joined together. In order to do that, go for operate, go for booleans, click on add, click on areas, select these 2 areas, and click on OK. Now you can find the area has been joined, the center line, the partition has been broken, and this has been joined together. The only thing that you have to do now is that you have to create a fillet of radius 40 mm at this location. In order to do that, go for create, click on lines, right? Click on line fillet, right? So this is the option. So select the two lines where the fillet needs to be here. So these are the two lines where my fillet needs to be created. Select these two lines and click on OK, and click on the fillet radius. The fillet radius is 40 mm. So click on OK. So you can find a small radius being created. So as I have created line, my fillet will be added in the form of line, which you can't see in the option areas. So in order to do that, go for plot lines. So I'll just zoom in for you. At this location, you can find my fillet being created, but in the form of a line. I need this fillet in the form of area. If I go for plot areas, I can't see this fillet. Only if I have plot lines, I can see the fillet, right? So I need to create this line fillet to an area. So in order to do that, go for create areas arbitrary by lines. So click on the three lines that is overlapping the joining the fillet, and I'll click on OK. Now you can find the area of the fillet being created. Now if you go for plot areas, you can find the fillet created, but still this fillet is separate from the other region. So I have to add this fillet to this region. So in order to do that, go for operate, booleans add areas, click on this area and click on add. So I can find the partition being vanished here, and the entire problem is getting converted into a single area. I'll just zoom out. This is a single area. All the individual partition, individual areas has been converted into a single area. So this is my modeling my problem. My model has been created. Next to modeling, that I have to mesh my problem. So in order to mesh, right? So I'll go for meshing. I'll click on size control. I'll click on lines. I'll click on all lines. Let me give a mesh of 50 mm, right? So 50 elements. So the number of elements for each line is going to be 50, right? Or else I'll do one more thing. So lines, pick the lines. I'll select the larger lines. So this one, this one, this one, and this one. These four are pretty much larger when compared to other lines. I'll click on OK. I'll click on the number of elements to be 100 and click on OK. And I'll click the shorter lines like this one, and here. These are the shorter lines. I'll click on these shorter lines. I'll give the number of elements to be 50, right? And click on OK. This is not that that you have to do as I do in this video. You can instead select lines, all lines, and click on just 100, and you can go on, carry on. You'll get the same results. There is nothing pretty much. If you change the elements like this, you're not going to get any very much good results. But this is one way to get a very good accurate mesh. I'll show you how, right? Instead of meshing, I'll go for mesh. I'll click on areas, and I'll click on free, and I'll click on this area where I need to mesh the problem. I'll click on OK. So the meshing is being carried out. So we're just taking a little bit of a time. Okay, so there is some warning, but please don't worry about that, and click on OK. So the meshing is being done here. So once the meshing is completed, the next step that I need to do is that I have to proceed with the boundary condition. So my boundary conditions are: this line is fixed, and I have a load of 2 × 10⁶ Newton acting at this point, right? So I'm going to do that two things. So loads, go for apply. I'm going for displacement on lines. I'll select this line. I'll click on OK. And Alt F, because it is a fixed, I'll select Alt F and I'll click on OK. And here, so this line is fixed, and I have a load of 2 × 10⁶ Newton acting at this in the upward direction. So I'll go for force on nodes, or I can select key points. Anyway, it is same. So I'll select this point. I'll click on OK, and I'll click on F of Y. And I'll click on force of moment, which is 2e6 Newton. So the unit of force is in Newton, which is upward direction. So I'll give positive, click on OK. So now if I solve the problem, there is going to be a error that is going to occur, right? So I'll solve the problem. I'll show you what is the problem with this loading condition. Then I'll show you how to rectify that. So as far as now, I'll just solve the problem. Click on solve, and I'll click on OK. And don't worry about the warning, just ignore it and click on yes, and solution is done. Now if I try to see in the displacement, I'll go for nodal solution. I'll show you how it is displaced. right? I'll just zoom in here, right? I'll just zoom in at this location. It is like only this point has been displayed, but actually that is not what actually that I need to happen. The actual thing which I require is that I need this entire line to be pulled in the upward direction, but here only the point where I have given the load has been pulled in the upward direction. So I need this entire line to be pulled. In order for this to happen, you have to give one more additional option in the pre-processing. I'll now show you what that is, right? So this is the problem. If you give only the loading and directly if you solve, you will not get your results. Only the point will get displaced, but this is not the actual condition that will happen. So in order to simulate my actual condition in which the entire line would be displaced in the upward direction, I have to give one more option. So I'll show you what it is. Go for plot and elements. Now I'll go for again pre-processing. Here there is an option called as coupling. Coupling has coupling equation. I'll expand that. There are lots of options, but as far as now we are concerned only about this first one, the coupled DOF. I'll select this one, and here what I need to do is that I need to select the nodes which are on this top line. I need to select the nodes only which are on the topmost line. So in order to do that, there are two ways to do that. One is that go for select entities, select the line, then select nodes attached to that line, and you can select the nodes. That is one way which I have seen in the previous video, but as far as now I'm not going to do that. The other way is that I'll just zoom at this location. I'll just go in zoom and I'll select a box and just create a box such that only the first node covers. I'm going to draw a box such that only the first the node attached to the topmost line will get selected. So this is how you draw a box. So even if you just get it a little below, you'll select all the nodes. This is not actually that I want. So I'll go for coupled DOF. I'll show you again. I'll click on box. So draw a box such that only the nodes which is attached to the topmost line will get selected. You can see how I'm selecting the box, right? Now if you leave the box here, you'll see only the nodes which are attached to the topmost line will get selected. This is another one simple way to do that. Now if you select OK, now you need all these nodes to travel equally in Y direction. So I'll just give a number, and instead of X, I'll select the U of Y and I'll click on OK. So you need all these nodes to travel together. Even one node of this line gets pulled, all the other node will go along with that. So that is the meaning of this coupled DOF, and click on OK. Next, I'll resolve my problem. Current plus and OK. And yes, don't worry about this, click on yes. Now I'll show you again how my problem has been modified. Again, general, deformed shape, deformed plus undeformed. Okay, so sorry, I'll show you in color, maybe that would be even better for you. I'll click on OK. Here you can find how uniformly my plate has been displaced. So instead deformed plate, you can find. So this is my first initial location, this is my final location. In previous case, only this point has been moved. Now my entire bar has been moved equally. So this is what actually I need. So save this image. So go for nodal solution, displacement vector, okay. Save this colored image. Even though you're not going to compare this value, just save this image, right? The thing that you are going to compare here is the maximum stress that is induced in the shaft. So in order to see the maximum stress, nodal solution, go for stress. Click on 1 mesostress and I'll click on OK. So I can see the maximum stress to be 100.233 in this case. So let me compare this with that of my calculated theoretical answer. So for that, let me give here. So this is my problem that I have modeled. So let me come there, count down. So my nominal stress, so my D by D ratio is 2 and my R by D ratio is 0.2. So D is the capital D divided by D. So 400 divided by 200 is 2, and my R by D, R divided by 200. So 40 divided by 200, which is 0.2. So for this 2 and 0.2, you can find here. So 2 is here and R by D 0.2 is here. So if you come here, 1.64 is my KT, which is stress concentration KT, theoretical stress concentration KT value is 1.64. Now if you calculate the nominal stress, which is load by area, load is 2 into 10 to the power 6 and my area is the smaller area. So among these two area I have to select the smaller area, because that will be the maximum nominal stress that you'll get. So which is pi by 4 into 200, sir, which is 63.662. If you multiply it with the 1.64, you'll get your maximums to be 104.405, and ANSYS shows you 100.223, which is very much closer in agreement. So 104 and 100 are very much almost closer with each other. So this is how you solve a problem of stepped shaft. So this is the problem of a stepped shaft with a fillet in tension. So a stepped shaft with fillet in tension. This is the second problem that we have seen in our case. Now we are going to see the third problem. So my third problem is a grooved shaft in tension. So this is my third problem, a grooved shaft in tension. Okay, now we'll see how to solve this grooved shaft in tension, which is the third discontinuity problem that you are going to see in this video, right? So my problem is this. So I have okay, so this is my grooved shaft which is fixed at one location, and I have again the same 2 meganewton acting at one direction. So my diameter is 400 and I have a groove at the center of radius 50 throughout the diameter, toward the circumference of my shaft I have a radius of 50. So if you subtract the radius 50 and 50 here, which will be 100. So if you subtract the 400 with 100, and you'll get the diameter of 300 at this location. From this point to this point, you'll get a diameter d of 300. So this length is 600, this length is 300, and this is made up of steel. Now this is a 3D problem. I'm going to simplify this 3D into a 2D problem, right? So in order to do that, so this is what you have done here. So using the condition of axisymmetric, I have converted this problem into a 2D problem, and these are my rectangles, and if I just rotate this rectangle about this vertical y-axis, I'll get this problem. So as I have already told you, the axisymmetric condition in ANSYS takes only rotation about y-axis. That's why I have rotated my problem about. So here my problem is about x-axis. So the reason that I have taken about y-axis is that the axisymmetric only works in y-axis in ANSYS APDL. So that's why I have just rotated in it. That's why I have kept the problem in about rotation about y-axis. So this is what I'm going to model, right? Now so I'm going to select the element, so which is again the same quad 4 node 182, which is the two-dimensional element which I'm going to use here. So I have used the concept of axisymmetric to simplify my model, and my material properties are steel, so which I can get it from here, or I have already given. And this is the modeling the problem, the dimensions of all the problem. And so this is 0, 0, 0. The diameter is 400, hence the radius is going to be 200. So this point is 200, 0, 0. This is 200, 600, 0. This is 0, 600, 0. 650, which is 200. So these are the coordinate value for all these points, right? And I have length and all these data is given, and load is given here, right? So once this modeling is complete, I have to mesh my problem, then I have to apply my boundary condition, which is a fixed and a load at this location. So let's see how to solve this problem of grooved shaft with axial loading with a tension in ANSYS APDL. So go for preferences, select structural, okay, click on preprocessor, element type, add, I'll click on add, and solid quad 4 node, okay. So I have to change this option to axisymmetric, and I'll click on OK, close, material property, material models. So I'll go for elastic isotropic, so 200, which is 200 E3 and 0.3. I'll click on OK, I'll click on close. Now I have to model. So modeling, so there are two ways. So either you can keep the key points, join them with lines, and then create the areas, or instead directly you can create the areas. So first, so this is the first area that I'm going to create, which is of length say 200 and height it is 600. So this is the first area that I'm going to create. So create areas by rectangle by two corners. So my starting point is 0, 0 and height 200, 600. So that's my first area. And my second area is the upper area, which is again 200, 300. So this is my second area that I'm going to create. So and my starting point for that area, that's going to be 0, 700, 0. So here you can see a radius of 50, which means this length will be a diameter. So this is the radius, hence this is going to be the diameter of 100. So hence this point would be 0, 700, 0. So 0, 700, 0, and my 0, 700, and my width is 200 and my height is 300. I'll click on OK. So this is my second. So the third, I need to create a groove here. So in order to do that, I'll create a rectangle here, then I'll create a circle, then I'll subtract that. Okay. So first I'll create two corners, and my height is 0, 600, my rect is 200, height is 100. Let me click on OK. So this is the rectangle created here. Now I'm going to create a circle at this location. So I'll go for circle, solid circle, and my length is 200, 650, and my radius is 50. So I'll click on OK. So this is the circle that is created here with this center point located here. Now I'll subtract this. I'll join these three areas and subtract this circular area. So for that, go for operate, booleans. First I'll add areas. I'll add this area. I'll add this area. Then I'll add this area. Except the circle, I'll add all these three areas. Now I'll subtract the circle from this area. So go for booleans, subtract areas. So the first area is the area that should be retained. Click on apply. The second area is the area that should be removed. And click on OK. So now my grooved shaft is model. So this is my model for groove shaft. So next I have to mesh this model. So for meshing, let me go for meshing. So size control, manual size, lines. So let me give all the lines to be 100 number of divisions and click on OK. Then I have to mesh. So mesh areas. Let me click on this and click on OK. So meshing is take place. Okay, so I can find the element count to be around 30,000. And so my quad is being formed. So it's taking a little bit of a time. Okay. We'll just wait. So now my entire area has been meshed with 100 elements on all the sides, all the lines. So just forget about this warning. Don't worry about this warning. Now I have to apply the boundary condition. My boundary conditions are fixed region at this line and an axial load of 2 meganewton at this location. So loads, apply displacement on lines. I'll select this line. I'll click on OK. I'll click all the way up 0 and I'll click on OK. And next, force of moment on nodes. I'll select this node. I'll click on OK. F of y direction, I have an axial load of 2e6, 2 meganewtons, so 2e6. I'll click on OK. Now, so one more thing that you have to do is coupling. So if you forget to do that, only this point will get displaced. So couple DOF, and so I have to select a box. So I'll just zoom this out. I'll select a box. I'll just draw a box such that only the nodes attached with the top line get selected. I'll click on OK. Let me give a reference number 2. Any number you can give it here. This is nothing to worry about. And the degree of freedom is the direction in which the node has to move, which is u of y. I'll click on OK. So all these nodes, even one of this node gets pulled, then all the other node will equally move in the upper direction. So I'll click on solve. So all this has been completed. Just have to solve my problem. Okay, don't worry about this. Click on yes. And here we are. Okay, my solution is done. Okay, so let me see. Let me fit the model. Let me see. Okay, deform shape. So instead of this, let me go to nodal plot. Let me see it in color. Okay. So I can see a displacement of 0.088213 mm. And this is not I'm interested about because I can't compare it with the theoretical answer. Anyway, save this image. Now I'll go to the stress value. So stress, and my stress intensity is 1 meso stress, and click on OK. So I can find the value 51.388 which occurs at this groove. So I need to compare with the theoretical answer. So my theoretical answer is, so groove to shaft with tension. So my D by D ratio, which is 1.3, and R by D is 0.16. So 1.3, D by D is 1.3, R is 0.16. So if you come along this, 1.91 is my KT value. Theoretical stress concentration is 1.91, which can be taken from the table. And the nominal stress value is load by area. So if you calculate, which is 28.294. So the nominal stresses, you have to get this groove, and using this D value, you have to calculate your nominal stress, because this is the actual nominal region where you don't have any groove. So this D is the region that you have to use for calculating the stress. So pi by 4 to D square, which is 300 square. If you calculate, which is 28.294, and so if you multiply it 0.91, my answer is 54.0415 is my maximum stress, and the ANSYS shows 51.388, which is a closer acceptance value. I can accept this value, which is closer in match with the theoretical answer. So this is all about solving the problem with discontinuity. So far we have seen 3 problems. So one is the plate with a hole, the another one is the a stepped shaft with a fillet, the third one is the grooved shaft in tension. So these are the three problems that you have seen. So one more thing, so this is anyway is a 3-dimensional model. I have seen only in the 2-dimension. So if you want to see this model in 3-dimension, so go for plot control. So under the plot, go for style. So in order to see this model in a 3-dimensional view, right? So go for plot control, click on style, click on symmetric expansion. So this is axis symmetry. So click on full expansion and click on OK, right? So I'll just show it here. So you can find the shaft in full expansion view, right? So how the shaft looks, so you can see it in full expansion view, the 3-dimensional view of my shaft. So this is how you can do. So you can also save this image. Go for plot control, right meta file, and save this image. So for the stepped shaft, this is for axis symmetric expansion. Similarly, for the plate with the hole, you can do this expansion and see the entire view. For that, as I have closed that, I'll open the session editor file of that one. So here I have the session editor file of this plate with the hole. I'll copy this. So the good practice to save an axis file is by saving the session editor file. Now go for I'm just plotting it here, and let me click on OK. So the entire problem, plate with the whole problem, is getting resolved again. I wanted to show you. So how to view this, the entire problem. I have modeled only the 1/4 model. I need to see the full view. So in order to see this full view, I'll go for plot control, style, symmetric expansion. So go for periodic or cyclic symmetry. Select this. So if you select, this would be the initial problem that you model. So now go for style, symmetric expansion, click on periodic or cyclic symmetry, click on 1/4. As you have modeled only the 1/4 of the model, click on 1/4 and click select. You'll see the entire model of the problem. Now you can save this image. Plot control, write meta file, and save the image. So this is how you view the full model of the plate with the whole problem. So that's all, folks, for this video session, right? So once again, we'll meet on another video tutorial. So you can always contact me for any doubts, right? Thank you so much and see you. Goodbye.